Hello, everyone. Welcome to our MADI 526 presentation. Today we'll be talking about the exothermic additive manufacturing filaments for improved mechanics of FDM parts. I will be talking, I'm Leah Dimitri, and so will Dan Parsons and Aiden Khan. I will be speaking on behalf of Fusion Forge. Fusion Forge is an additive manufacturing consulting and vendor company that provides high quality FDM or fused deposition modeling printed components to our clients. We focus on selling high quality goods, whether it be printers or filaments, and also providing services to clients that span the aerospace, automotive, or even biomedical industry.
Thank you for the introduction, Leah. For this specific project proposal, we propose the creation of a polymer metal oxide filament mix that utilizes the heat upon exposure to air and the resulting exothermic oxidation reaction to sustain a high degree of interlayer adhesion in the Z direction to enhance the mechanical properties of 3D printed parts.
Now I'm going to go a little bit into our problem statement. As Aiden kind of touched upon, the issue that we're addressing is poor interlayer adhesion, specifically in the Z direction, and this can cause a weakening of different mechanical properties. So we see a reduction in tensile strength or even stiffness. There's different causes that can relate to this, but two of the main causes are improper thermal control and moisture-induced weakening. First, regarding improper thermal control, nozzle temperature plays a very important role in interlayer adhesion. Nozzle temperature, an increased nozzle temperature is going to improve the elasticity of the polymer, which can therefore result in a welding effect between different layers. One may think that increasing the nozzle temperature would therefore improve interlayer adhesion. However, the issue isn't as simple as that. This is because if we increase the temperature too much, we can see polymer degradation, which of course is something that we want to avoid. Also, it's important to note that the molten filament is going to be placed on top of a pre-existing layer, and this pre-existing layer can have experienced some sort of rapid cooling. And when this occurs, thermal shock is going to happen. And thermal shock is going to hinder polymer mobility, which is going to compromise the ability for layers to adhere. Moisture-induced weakening can also rapidly reduce the mechanical strength. And this is essentially because the water can hinder the ability for the polymer chains to intertwine and therefore weld together, which is a substantial problem resulting in compromised interlayer adhesion. So therefore, our project aims to address both temperature and environment-related challenges that affect interlayer adhesion by developing an exothermic filament, which will be kept under vacuum conditions and printed within an oxygen chamber. And this will provide heat, improving the interlayer adhesion, and also a controlled environment that will prevent excess moisture.
So going into some of the existing technology that exists to address this problem, there isn't any really single solution that has been developed by any company. It's kind of just commonly accepted that Z direction strength is an issue with FDM 3D printed parts. Some ways to address this are that you can kind of design around the problem. So one way of doing this is that you can make sure that you're printing your part in an orientation so that the stresses that eventually get applied to it are focused on the XY direction of the printing plane, so that you're taking advantage of the full strength of the material where your part needs it the most. Another method, as we can see on the right diagram here, is reinforcement. And basically the idea here is that you incorporate something like a metal bolt into the design of your print so that it can be strengthened in the Z direction that way. And then finally, you can use composited materials such as carbon fiber or glass-filled 3D printing filaments. And the idea here is that you're kind of just increasing the strength of your part in all directions, Z included. And then these are all kind of band-aid solutions, though. They don't really address the core issue of interlayer adhesion. And so there has been some light research on actually addressing this issue, such as a research paper where a group used a diode laser to melt their previous layer before they lay down a new layer on top of it. But this didn't really work out. They had a lot of issues with defects and whatnot. So currently there is no like solid solution to the problem of interlayer adhesion in FDM parts.
And now to explore the preliminary work that we have done in regards to this project. We began by conceptualizing a mixture of pure calcium metal, suspended in an ABS filament, which is then used. So the pure calcium metal, once extruded from the nozzle of the 3D printer and exposed in the presence of oxygen, the resulting exothermic oxidation reaction releases roughly 635 kilojoules per mole of energy, which aids in the interlayer adhesion by sustaining a relatively high temperature for each layer printed, so that the successive layers printed on top are better adhered to each other. Current work, which we are building off of in the storage methods of 3D printing filaments, include vacuum sealed bags, just as a method of saving space. And so now our conceptualized work expands upon those vacuum sealed bags to in addition to the vacuum sealed filament spool bags, creating a vacuum within the entire pump and out until the nozzle of the 3D printing machine, to prevent premature oxidation of the metal polymer filament.
So just to go a little bit into the impact that this novel technology would have to our company. So first, we need a team in order to make it happen. And in order to lead the project, we're going to have a principal investigator. Beneath the principal investigator, we're going to have a team of engineers. So the material scientists will largely be working with creating the polymer composite filament. The mechanical engineers will therefore be developing the FDM printer, and the manufacturing engineers will really be working on optimizing that scale-up process. We also will have business analysts, marketing, and a legal officer that will help kind of deal with patents, any type of IP that we need, and kind of really drive that commercialization process. So the funding that we are asking is going to cover the cost of our development. So first, we need to pursue research and development in order to create a filament, and this will be around 55,000. And then to cover the cost of materials, we need about $38,000. And then to develop the FDM printer itself, this will require about $35,000. And then we're going to perform testing and validation with a budget of $18,000. And in order to cover the cost of our team, such as their salaries for 1 year, this is going to be about $1 million. And the miscellaneous costs, which are going to include any consumables or rent space for our R&D facilities, would be about $90,000 for the first year. So cumulatively for 1 year, we are asking for about $1.3 million in order to achieve our goals. And given the increased demand of our product, because we address an inherent issue with FDM printing, which is weak interlayer adhesion, we expect a projected profit to be about 2 million, resulting in a return on investment at 52%. It's also important to take into consideration that we will do some minor rewiring with our company. So we need revisions of current safety protocols in order to include safe handling of gases, such as pressure monitoring and ventilation, to mitigate any risk of fire or explosion. We also want to establish reliable supply chains where we can source our heavy metals, specifically in areas such as China, Brazil, or India. And also our technology will have impact to the environment and society. So environmentally, mining of these metals may lead to excess carbon emission. However, it's important to note that our technology is providing a more sustainable manufacturing process that isn't as energy consuming and wasteful as traditional manufacturing that is out there. And as for our impact to society, the FDM components can be used for high performance applications. So it's really opening the field of FDM to these different areas. And we can also target a niche group of people, such as those in industry that are looking to create more affordable, strong components, but can't really go towards expensive metal additive manufacturing.
Okay, so for the proposed workflow of this project, our goal is to develop an exothermic filament that enhances the mechanical properties of FDM 3D printed components. We envision that this filament can be sold as either standalone systems or with our custom-made 3D FDM printer with an enclosed oxygen chamber for optimal performance. We are going to monitor these works, the work in the outcome in the four milestones we have here. Milestone 1 being the formulation of an optimized film. Milestone 2, the development of a compatible printing setup. Milestone 3 is the scale up of the manufacturing process of both the printing setup and the film. And milestone 4, lastly, being the commercialization of our produced products.
All right, so for the objectives for this process, our primary goal is to determine the loading of calcium required to keep our compositing material above TG. This is kind of a baseline that we want to use because we can surmise that we're not going to have much of a difference if our polymer is below TG. And then furthermore, we need to investigate how including this calcium affects mechanical properties beyond interlayer adhesion. Second, we want to research how difficult it is to prevent this reaction until you're actually printing it. So in otherwise, how practical is it to produce it and then to transport to customers? And thirdly, we want to formulate a consistent product, whether that be the material, the storage system, or the 3D printers that we're making. We need to have something that can be brought to different customers and work consistently. So going into our first milestone, which is the formulation of a filament, as we mentioned before, we want to develop an exothermic powder-filled filament that can keep our polymer above TG until the next layer is extruded, which in most cases we say is approximately 5 minutes for a normal size 3D printer. Worth noting is that metal powder-filled filaments do actually exist, as we can see on the right, with a magnetic composite material. So there's some research already done in this field. Furthermore, we want to ensure that the percolation of our additive is low enough to not interfere with normal printer operations, so we don't want it to cause jams or anything in our nozzle. And then finally, we want to ensure that the reactivity is low enough to prevent reaction until the consumer is actually printing.
So our second milestone is to create a prototype that is functioning. So here we have a schematic design of what we would expect our FDM printer to look like. And it's important to note that it would incorporate two main components. So the first component is a vacuum sealed chamber, and the second component is an oxygen enriched printer chamber. So as you can see on the schematic to the left, the filament will be kept under a vacuum, and this is to ensure that any premature oxidation would not occur. And then the filament would be printed into the chamber, and the chamber will be rich in oxygen. So it's going to be hooked up to an O2 line, an O2 gas line, and this is basically in order to control the rate at which the oxygen is filling the chamber, so that we have the oxidation reacting occurring at ambient condition. And then lastly, the exothermic reaction will occur once it's printed via oxidation, therefore improving interlayer adhesion.
Our third milestone is that of the process scale-up. So basically, this entails developing or modifying a bulk processing line to manufacture our filament. So the two main things that we could think of that would have to be changed are that A, we would have to keep certain parts of the extrusion line under vacuum. to prevent premature oxidation of our calcium. And then furthermore, the cooling step of filament after it's extruded is typically done with water or air cooling. In this setup, we would have to use something else as both water and air react with calcium. And so some suggestions are that we could use oil if we want a liquid phase bath to cool our filament in, or we could use inert gases instead of air. Some suggestions would be argon or nitrogen.
And then our fourth and final milestone is the actual commercialization of our product. Further parametric studies can be done to determine the exact ratio of an example metal and polymer filament for various applications to cut down on waste and to improve mechanical properties. Determining what those mechanical properties are will also advertise to certain industries for a variety of applications what mechanical properties one field is looking for versus another will allow us to target certain industries to advertise our product. And also collaborating with current industry partners to perhaps outfit existing 3D printing models with our augmentations to run various printing jobs. And finally, commercialization is proposed to begin once the generated profit is double the initial investment, which corresponds to roughly a value of $2 million.
So finally, with some challenges and risks for our project, on the challenges side, we have that 3D printing filaments are already a temperamental product. So adding more factors that kind of make it more complex can compound this issue. Um, Furthermore, formulation would be difficult because it's tricky to manage the heat release of such a product, and so it'll be difficult to kind of find a way to make sure that we're keeping within our temperature range. And then also scale up and commercialization is difficult because there are many more factors involved in kind of ensuring product quality is high. When even normal 3D printing filaments, there's already a lot of things you have to keep track of. And then on our risk side, even after successful formulation and implementation are achieved, it could be difficult to commercialize this product because there's a lot of different things that have to be managed, such as the premature oxidation of the product. Furthermore, it is a slightly niche product because it only services a particular part of the market, but we believe that does solve an issue that has yet to be solved. So there's a lot of potential regardless. And then furthermore, there's some potential safety risks depending on the exact additives used to cause your exothermic reaction. In the case of calcium, it's probably relatively safe, but if more reactive variants are pursued later down the line, there's potential for things such as fire hazards and other safety risks.
So finally, just to conclude with a summary of our proposal, we propose the development of an exothermic additive for the creation of FDM parts that has the potential to impact a variety of sectors depending on their applications. We also propose to outfit existing and to be developed 3D printer models with our attachments to facilitate the exothermic oxidation of metal polymer filaments. Lastly, we'd like to thank you very much for your time today, and we wish you the best. Thank you.